All right, so now we're doing 31 through 40. So 31 is secant squared theta over secant squared theta minus 1. We're supposed to show that that's equal to cosecant squared theta. So I'm going to start on the left side here. Always check for identities when you have a 1 plus or minus trig function squared. So secant squared minus 1 is a rearranged Pythagorean identity. So we have secant squared on top, and this is tangent squared theta on the bottom. And then let's rewrite in terms of sine and cosine. So 1 over cosine squared theta over sine squared over cosine squared. Take that out of its ugly complex fraction. 1 over cosine squared theta times cosine squared theta over sine squared theta. Cosine squareds cancel, and 1 over sine squared is cosecant squared theta. Number 32, we have tangent squared theta times sine squared theta is equal to tangent squared theta minus sine squared theta. I always think that's kind of interesting. That two things multiplied are equal to the difference of the two things. That's strange. So which side do you start on? There's usually more math to do on the addition or subtraction side. So let's go to this side. Sine squared is, or tangent squared is sine squared theta over cosine squared theta minus sine squared theta. You can put it over 1 if you want to. We need to get a common denominator. That's what I mean by there's more math to do. We can adjust this a little bit. Over here, we can just, if I start on the multiplication side, I'd be kind of stuck because nothing really would cancel. Okay, so the common denominator is cosine squared. The first fraction has the denominator, needs no adjustment. The second fraction would need to get multiplied by cosine squared over cosine squared. So that becomes minus sine squared theta cosine squared theta. And I don't see any identities up here, but I should also check for factoring. I can factor out a GCF, sine squared theta. That would leave me with 1 minus cosine squared theta over cosine squared theta. Now we're trying to get tangent squared times sine squared. I see tangent squared right here. Sine squared over cosine squared is tangent squared theta. And I also see sine squared because 1 minus cosine squared is sine squared theta. All right, so that finishes 32. On to 33. So 33 says sine theta plus cosine theta squared plus the quantity sine theta minus cosine theta squared should just equal 2. So to me, this is an easy proof, even though it's going to be annoying to write out. It should just be that we FOIL everything and find things that cancel. So you've got to be able to square a binomial. So squaring a binomial is the first term squared plus 2 times the product of these two parts. You're going to get a sine, cosine, sine, cosine. So plus 2 sine theta cosine theta plus the last term squared. And then when I add to that, I'm coming down here just because I don't want to go into my other space. When I square this binomial, the only difference is that I get sine squared theta minus 2 sine theta cosine theta plus cosine squared theta plus 2 minus 2 sine theta cosine theta add up to 0. Sine squared plus cosine squared is 1, plus another sine squared plus cosine squared is another 1, and 1 plus 1 is in fact 2. Number 34, we have sine theta plus cosine theta times tangent theta plus cotangent theta equals secant theta plus cosecant theta. And remember, you can give yourself a preview for where you should end up. We should end up with like 1 over cosine plus 1 over sine. You're not allowed to work on both sides and meet in the middle, but you are allowed to work on the right side or the other side and see where you're supposed to be getting to. Now, I want to remind you that sine theta plus cosine theta is not equal to 1. It has to be the sum of the two squares. So we can either FOIL this right now, or we've added tangent and cotangent quite a few times now. And usually when we add tangent and cotangent, it simplifies to like a really nice expression. So I think I want to start there. It's hard to know sometimes what the most efficient path is going to be. I'm just sort of remembering from all the other proofs that we've done so far in this chapter that when I've had multiplication involved, it has been convenient to add these two together when they're in terms of sine and cosine. So if you went the FOILing route to begin, that's probably fine too. You just might have a couple more steps to write. I don't know. Or maybe I'm doing it the long way. We're about to find out. Okay, so when we add tangent and cotangent, the common denominator is cosine theta, sine theta. The first fraction would get multiplied by sine, so you're going to get sine squared. And the second fraction by cosine over cosine, so you're going to get cosine squared. So yeah, these add up nicely to 1 over cosine theta, sine theta. So because that's 1, we can multiply these expressions together and say we have sine theta plus cosine theta over cosine theta times sine theta. Because this, again, was just 1, so we don't have to show like the times 1 thing. Okay, now what am I going to do there? Again, this is where it's helpful to have shown myself a preview of like, wait, I'm trying to get 1 over cosine plus 1 over sine. I'm trying to get two fractions separately added together. We're used to using our Hart method, our division here, when there's just one single trig function down here. But this is a single term, so I'm still allowed to use the Hart method. And again, we've done that before too. It's just, it doesn't look as nice. But that helps because you're going to do sine theta. You're separating this out. Sine theta over cosine theta sine theta plus cosine theta over cosine theta sine theta. So these cancel out sines, and these cosines cancel out. That's 1 over cosine theta plus 1 over sine theta. And that was one of the places I was trying to get to, right? So then finish it off. This is secant theta plus cosecant theta, which is what we were trying to prove. All right, number 35. Find my pen here. There we go. Number 35 is tangent theta minus 1 over tangent theta plus 1 is supposed to equal 1 minus cotangent theta over 1 plus cotangent theta. So I don't think it matters which side you start on for this one. In either case, because there are no trig identities, none of these things are squared, I think our best bet is to write in terms of sine and cosine. I do not multiply by the conjugate because that doesn't really help me get from tangent plus 1 to 1 plus cotangent or something like that. So I'm going this route. Let's start on the left side. So sine theta minus 1. Oh, no, sorry. I was distracted by my bad pen writing there. So sine theta over cosine theta minus 1 over sine theta over cosine theta plus 1. I'm going to use the multiply by 1 trick, which clears out the complex fraction. Multiply by cosine theta over cosine theta and distribute that through each term, top and bottom. So that's going to make this sine theta minus cosine theta over sine theta plus cosine theta. Okay, now this is where it's like, okay, I'm stuck. Do I multiply by a conjugate? Again, no, because the right side is not just in terms of sine and cosine again. So what are we trying to get? We've done this trick before too, on a couple of other worksheets. I have sine minus cosine. I want 1 minus cotangent. Give yourself a preview. What is 1 minus cotangent? It's 1 minus cosine over sine. And 1 plus cotangent is same idea. I have a minus cosine and a plus cosine in the position where they should be. I want them to be divided by sine. So make that happen. Multiply by 1 over sine, top and bottom. Or you could say divide by sine, however you want to think of that. But if you do that, everything kind of falls into place because, look, you get sine times 1 over sine is 1, minus cosine theta over sine theta, which was what we were trying to get to. We got that piece. And same thing's going to happen on the bottom. Sine times 1 over sine is 1, plus cosine theta over sine theta. So a neat little trick there to get you 1 minus cotangent theta over 1 plus cotangent theta. And that's not the only route to get from the left side to the right side, but it's just the route that I tend to see. If you saw something else and you wanted to check to see if what you did was legal math, just stop by office hours and let me know. All right, here's this fraction again. 1 minus tangent squared theta over 1 plus tangent squared theta. So I already know what my first step's going to be. We're trying to make this equal to 1 minus 2 sine squared theta. First step, we've seen this a few times, is to change the Pythagorean identity to secant squared theta. Next step is to divide. 1 over secant squared is cosine squared minus tangent squared in its quotient identity form, divided by secant squared. So how about times cosine squared theta over 1? Because we've done this a couple of times, that's why I skipped the initial step. If you want more of a breakdown, go back to the previous problem that had the same fraction. This becomes cosine squared theta minus minus sine squared theta. And we practiced this a few times earlier in the page. I think it might have been 29 and 30. If we want to get 1 minus 2 sine squared, we replace cosine squared with 1 minus sine squared. And then we combine like terms. So you can see you're seeing a lot of the same expressions over and over. That's because we only have so many identities to work with. And unless we start coming up with proofs that are like really super long, we kind of keep recycling the same bits from proofs. All right, so 37 is cosine theta plus 1 over sine to the third, that's unusual, equals cosecant theta over 1 minus cosine theta. So I say this is unusual because sine to the third is usually reserved for factoring, but there's nothing else to factor with it. So you could start on this side, or you could try starting on the right side. The only idea I have, well, no, I really don't think it matters. Let's start on the right side and see if we can manage to get sine cubed. So first thing I see is this is 1 over sine theta over 1 minus cosine theta. Okay, so that's kind of weird. This is like saying I've got 1 over sine theta times 1 over 1 minus cosine theta. All right, so that's 1 over sine theta times 1 minus cosine theta. I don't think I want to distribute those because I think that I might want to use some conjugates here. Because remember, use the left side as your hint. I've got a 1 minus cosine theta in the bottom fraction. I'm kind of stuck, and the left side still has sines and cosines, so this is a good indicator to multiply by the conjugate. The conjugate of 1 minus cosine is 1 plus cosine, and take a look, you want 1 plus cosine on the left side eventually. All right, 1 times 1 plus cosine is 1 plus cosine. Now be careful with your algebra rules here. You're multiplying 3 things together. I'm going to multiply these 2 conjugates together, and the sine theta will just be along for the ride. 1 minus cosine times 1 plus cosine is 1 minus cosine squared. That is convenient because 1 minus cosine squared is sine squared. Let's flip the order too. Instead of 1 plus cosine, cosine plus 1 over sine times sine squared. And yeah, that's cosine theta plus 1 over sine cubed. Now, if you check the key that I posted, I believe I started on the left side and almost went in the exact reverse order. I separated these out, and then I probably rewrote sine squared as this, and then I factored, and then I canceled. So I think this, maybe starting on the right side, is a little more close to what we've been doing. Okay, 38. Sine theta over 1 minus cosine theta is equal to cosecant theta plus cotangent theta. I believe we've had this in our notes on other worksheets, or if not this exact problem, something very close. So let's start on the right side for this one. 1 over sine theta plus cosine theta over sine theta already has a common denominator. But then you get stuck because there are no Pythagorean identities, there's nothing to factor, and everything's already rewritten in terms of sine and cosine. So that's your hint to multiply by the conjugate of 1 plus cosine, which is 1 minus cosine. Conjugates multiply together nicely. That becomes 1 minus cosine squared theta. To be most efficient, don't multiply the non-conjugates through, meaning don't distribute. Just leave it like that. Because 1 minus cosine squared is sine squared. Leaving the sine theta out here allows you to see that you can cancel a bit. So this sine theta cancels with one of those, and I'm left with the left side of the equation, sine theta over 1 minus cosine theta. All right, 2 more problems. 39 is tangent theta over secant theta plus cotangent theta over cosecant theta equals sine theta plus cosine theta. Here's another one we should work on the left side and rewrite in terms of sine and cosine. So sine theta over cosine theta, instead of dividing by secant theta, I'm going to multiply by cosine theta over 1, which is the reciprocal of secant, plus cosine theta over sine theta. Instead of dividing by cosecant, multiply by its reciprocal, which is sine over 1. That's a short little proof because things cancel and you're left with sine theta plus cosine theta. All right, last problem in this group. Sine theta plus tangent theta over 1 plus secant theta is supposed to just equal sine theta. No Pythagorean identities. I've got a mixture of trig problems, so I'm going to rewrite in terms of sine and cosine. So tangent gets rewritten, so does secant. Now I have a complex fraction, so I'm going to clear it out by multiplying by the denominators that I see in the complex fraction, which is just cosine. Multiply by cosine over cosine, and you get sine theta cosine theta plus sine theta over cosine theta plus 1. Factor out a sine theta. This one feels familiar. Did we have this exact problem earlier? It's possible. Factoring out a sine allows you to cancel cosine plus 1s, and you are in fact left with sine theta. All right, we've got one more group of 10, and then this worksheet's finished.